So now that we have formally solved the differential equation, let us look at an important concept, how, requiring some physical boundary condition on the solution leads to quantization of energy. So we're going to look at the quantization of energy. So the series solutions, so let me remind you what the series solutions look like. The series solutions, like for example, phi 0 of x, which is going to be like an even function. Now these solutions, this series cannot go on forever, because if they go on forever, then we can argue that these won't be divergent, these won't be if they go on forever, then these solutions will not give a physically realistic wave function. So let's look at two consecutive terms in these series. So if I take the term, which is a xn plus 2, then its coefficient is a n plus 2. And if I compare it with the term, which is x to the power n, and its coefficient is an. Now, if I use the recurrent relationship that we have between an plus 2 and an, then we have this is equal to 2n minus lambda minus 1 divided by n plus 1, n plus 2. And this will be multiplied by x squared. Now for large values of n, when n becomes large, we see that this ratio goes to 2 over n x squared. So this is these series are convergent series if they go on forever. But the problem is that is the following. This ratio between consecutive term is the same as the ratio between consecutive terms of the following function. So if I take the function exponential to the power positive of x squared, so this is basically going to be given by, say, n goes from 0 to infinity, x squared to the power n divided by factorial n. We can of course write this as, say, n 0 to infinity, but where n only takes value in the even positive numbers. Then we can write this as x to the power n divided by n by 2 factorial. So if I look at this expression and I compare two consecutive terms for large n, then we see that those consecutive terms will have this form. So we see that these functions, asymptotically, they look like this function, and therefore at infinity, these functions will diverge, and therefore they will not lead to a wave function which is normalizable. So that is a problem. A second problem is that, this solution that we have doesn't put any restriction on the value of lambda. But we already saw that lambda has to be at least positive. So how do we reconcile these two problems? So these two problems are reconciled if the series don't go on forever, but for some value of n, they terminate, similar with this series. That is, if at some point, this numerator becomes 0. So there should be some value of n for which this is 0. So the condition is that this thing goes to 0. So the condition becomes lambda 2n minus lambda minus 1 becomes 0 for some value of n. And if you solve this, we find that lambda can take, its value should depend on n, and it's given by 2n plus 1. Now, if we now go back to our original variables, we see that this leads to the following values of En, the energy of the oscillator. The energy of the oscillator remember, it's given by lambda times half h bar omega, but lambda is quantized because of this this condition. Therefore, the energy will be given by, let me just write it down here. The energy is given by n plus half times h bar omega. So these are the energies of the simple harmonic oscillator. So let me recap the argument. The argument is that our wave function should be normalizable because it's a bound state, and therefore our solution phi 1 and phi 0 should go to 0 as x goes to plus or minus infinity. But that only happens if the series terminates at some power of n. And for that to happen, this has to be the numerator of the recursion relationship has to be 0 at some point for some value of n. So if you look at that condition, this condition, this means that the energy lambda has to be given by this number, and therefore this leads to a quantization of energy. So in this formula, n goes from 0, 1, 2 to any positive integer. So this is perhaps the most famous equation in quantum mechanics, and we should dwell for a few minutes and discuss this. So some of the interesting aspects of this is, what we have shown is that the quantization of energy is a result of the bounded nature of the system. If the system was not bounded, and therefore we didn't have to require that the wave function be normalizable, then we would not have this quantization condition come about, because then we would not have to terminate the series. And therefore, this is a generic feature in quantum mechanics where the quantization of energy is related to the bounded nature of systems. So for example, if you take the solar system and if we could measure the energy of the system very, very precisely, we would find that the allowed energies are not continuous, but they are discrete. So when we're dealing with macroscopic bodies, we can't really measure those fine energy differences. But for very small systems like the atomic systems, we are able to measure those different energies. The other thing is that for large values of n, we get n is proportional to n times h bar omega, because when n is large, we can ignore this factor, this of half. So this is precisely the Planck hypothesis. Recall what Planck assumed. Planck assumed that in a black body, if you have a black body, then the molecules on the wall of the black body, they were oscillators, but they could oscillate with some discrete energy levels, if it's a frequency is omega, the energy was allowed to be n times h bar omega. So thus we see that the simple harmonic oscillator naturally leads to the Planck hypothesis. So it naturally leads to it provides a justification for the black body radiation and Planck formula. So number 3 is that, of course, Planck's idea inspired Einstein to assume that that photon have energies given by h bar omega, and that, and the Bohr idea that, if we have two energy levels in an atom and they are separated by h bar omega, then the atom, if it's in the lower energy level, it can absorb a photon and jump up to a higher energy level. So this tells us that the energy levels of the simple harmonic oscillator n h bar omega, we can think of these n's as particles, that is photons, that are being absorbed by the simple harmonic oscillator. Of course, here we are not providing with a mechanism in which the harmonic oscillator can interact with light, but that is something that is done in more advanced quantum mechanics courses. But this gives a justification of thinking about light as a particle and the excitation of the harmonic oscillators as being the harmonic oscillator absorbing quanta of photons. And lastly, note that when n is 0, the ground state of energy, or the vacuum energy of the harmonic oscillator, is half h bar omega. And see that this is not equal to 0. So this is a very important thing, and it's very peculiar to quantum mechanics that the ground state energy of a system is not 0. And this is related to what we'll see is related to the Heisenberg uncertainty principle. You can argue from the Heisenberg uncertainty principle that if the energy of the ground state was 0, then it would violate the Heisenberg uncertainty principle, and we would be able to determine both the momentum and the position of the harmonic oscillator with arbitrary precision.